Hello, my name is Rob Reynolds. Welcome to Mat-073. And today we're going to be looking at section 6.5, rationalizing the denominator of radical expressions and how to simplify. So we already know if we have 5 over the square root of 3, we can multiply this by a unique value of 1. And in this case, the value of 1 would be the square root of 3 over 3. This is a nice technique that you should already be familiar with. What I'm going to be teaching you today is what happens if we have 5 over 2 plus the square root of 3. It's not as easy as you may think, because if we were to try to use the same technique, we wouldn't actually accomplish our goal, which would be to rationalize the denominator, because we'd still end up with a radical in the denominator if we distribute both terms. And so we're going to talk about the word conjugate, which means change the middle sign. So for our first example, we're going to take you back to just remind you strategies that did work. We're multiplying by the square root of 7, and we can just multiply. Remember, the square root of a times the square root of b is just the square root of ab. So I'll use that first property here, the square root of 35 over 7, because the square root of 7 times 7 is really the square root of 49, but that simplifies. So that's something that you already know how to do. It also works for cube roots. So the cube root of 3 divided by the cube root of 25. A little bit harder because we need to find out, well, you could multiply by 25 squared. But that's probably not the easiest way to do this because the numbers get pretty large. I don't want to have to mess around with the cube root of 25 cubed, which, by the way, just is 25, but up top I got a mess. I would end up multiplying this 3 times 25 squared, and I get a massive, huge number. So to avoid big numbers, I'm going to try to show you a strategy. If you can try to remember to break this down, 25 can be rewritten as 5 squared. So I think the strategy, I'll say the word or. So maybe we'll finish that top so you can see that it's really easier if we break that 25 down. So I'm going to try to remember to break this problem down to a prime base. And when I say prime bases, I'm looking for numbers like 2, 3, 5s, and 7s. So 25 is not prime. I'm going to break that down to be 5 squared. So instead of creating, see, now remember, I needed the cube root of 25 cubed in order to get to the 25. Down here, all I need is one more 5. The cube root of 5. So there's my factor of 1 that you're always going to be looking for. So I'd rather use this pink one opposed to this yellow one, because the yellow value of 1 is much larger. So I think we work better with smaller numbers. So up top we get the cube root of 15, and down bottom we just get a 5. Because why? The cube root of 5 squared times 5 is really just the cube root of 5 cubed, which is just back to the 5. So we're done. There's the final answer. And if I would have worked it up here, life would have been miserable. I would add a huge number. 25 squared times 3 is 1,875. I mean, I'm already afraid of that. And I think I've already convinced you that that's not the direction that you want to head into. But if we're clever, we could still get to the same answer. So this would be 125 times 15. If you multiply those two together, I think you get the 1875. And the cube root of 125 is 5, because 5 cubed is cube roots of 15. And then I could cancel this 5 with this 25, giving me just another 5 down below, and the cube root of 15. Much harder. So I think I've convinced you prime bases is the way to go. Let's see if the author agrees here. There's the first one, and yes, they immediately changed this 25 to be 5 squared. They wrote it a little bit differently, but the same principle here. So let's try this again. This is the square root of 5 over the square root of 3x. There's an invisible 2 out there that we normally don't write, but I need to create another 3 and another x. I usually don't write this step, the square root of 3x, this whole thing squared. I just usually jump to 3x, because the square root of anything times the square root of itself is just the answer. So you can avoid this center step in showing the work. But if you multiply the denominator by 3x, you have to multiply the numerator by 3x, because remember, the whole goal is to multiply by a yellow 1. And up top, we'll just get the square root of 15x, and I don't think I can do anything. Although it looks tempting to cancel the 15 and the 3, we cannot. So the final solution is, yep, just leave it. The square root of 15x divided by 3x. Let's repeat this process again. I'm going to leave the 3y alone, but I need to create a yellow 1 again. So I've got 1, 4. I better create 2 more. I've got 1x. I better create 2 more. And I've got 2 y's. I better create 1 more. So if you multiply the bottom by, I'll just say 16, because that 4 squared in the denominator really is 16. X squared y. I'll end up with a denominator that turns out pretty nice. You know, I just noticed I broke my own rule. Instead of going up to 16, I wonder if I could have rewritten this and avoided some of those big numbers. This is really the cube root of 4, which is really the cube root of 2 squared. So really I'm just lacking another 2. Because this is going to take this, the cube root of 2 squared, times this cube root of 2, and that will give me the cube root of 2 cubed, which would just be a 2 out here. So that looks a little bit easier, and keeping the numbers a little bit smaller. So again, remember changing this 4 to 2 squared for a prime base. We'll keep the numbers a little bit smaller. Looking at the denominator, again, I've got an x times an x squared, so that's going to be the cube root of x cubed, which will simplify to just x. And the same thing happens to the y term here. That's y times, or excuse me, y squared times y, so it's the cube root of y cubed, which is just y. So the denominator turns out to be rational, which is my goal. The numerator is not pretty, but I think I just have to leave everything. How do you know that you're done? Well, you're done when the exponents in the numerator are smaller than the root. So this is pronounced the cube root of 2x squared y. So, and remember the exponents up here, which we never write, 2 to the first, but there's really a 1 here and a 1 here. So as long as those green numbers are smaller than the pink 3, then I'm done. Let's see if the author agrees. 3y cube roots of... Oh, it looks like I forgot to cancel my y's. So the y's cancel here. These y's should have canceled. I can't cancel anything underneath, but yeah, I could have canceled those y's. So just 3 cube roots of 2x squared y over 2x would be my final solution. So yeah, 3 over 2x. Good, so reducing. Let's take a look at number 11. 6 is not a prime base, but I can't break down 6 to be anything. I get 2 times 3, but I don't want to go there. But I can't write this as 2 squared or 3 squared, so I'll just leave 6 alone. I'll multiply by 2 more 6's. So that's going to be a 36, or 6 squared, but I could write a 36 up top. And I've got actually too many of these. So this is 4 doesn't divide by 3, so I'm actually going to go up to 6. So I need 2 more of those in order to get up to, because what I'm looking for is the cube root of x to the 6. So that 6 will divide by 3 evenly, and that'll give me an x squared in the answer over here. In fact, finishing the denominator, it's the cube root of 6 right here times the cube root of 6 squared, which is the cube root of 6 cubed, which is just a 6 in the denominator. The numerator, I'll just multiply it together. 36, oh, I've got an x squared here too. 36 times 2 is 72. I'll see if I can simplify that in a moment. Y to the 4th, which again breaks my rule because exponent is higher than the root, and x squared. So there's a couple different things I think I can simplify. Let's start with the cube root of 72, which is the cube root of 8 times the cube root of 9. And interestingly enough, the cube root of 8 simplifies, but the cube root of 9 does not. The 4 can be broken down to be the cube root of y cubed and the cube root of y. And I don't think I can do anything with that cube root of x squared, so I'll just leave that. So the numerator, I'm leaving the 6x squared alone, but the cube root of 8 is a 2. The cube root of y cubed is a y. And then I think everything else I better just leave alone. I can't simplify this, this, or this. So I'll just write all the blue terms underneath the cube root and just make it 9y. How about, I usually put these x's first because alphabetical. 9x squared y's. I could have said 9yx squared, doesn't matter. And then it looks like the 2 and the 6 were reduced. So how about y, cube roots of 9x squared y, all divided by 3x squareds? Final answer, and we'll see if the author agrees. Yes, they do. And I wrote a huge space in between this y because I didn't want you to think that it was a y cubed and then the square root of 9x squared y. So make sure that your final answer looks like y is being multiplied by the cube root. So if I could just refresh your memory just a little bit what's going on here. A good rule to follow is if you're in the numerator, go down. If you're in the denominator, go up. Let me explain what I mean. If you're in the numerator and you're trying to simplify, I want you to go down. So 4 doesn't divide by 3, but go down to 3. Because this is the cube root of y cubed times the cube root of y. So if you're in the numerator, we're going to go, and by the way, we are in the numerator here, because there's a 1 down here. This will just be y, cube roots of y. So remember, this exponent, whenever it's larger than the root, then I can simplify it. So the rule is, if you're in the numerator, go down. But if you're in the denominator, if I flip this problem to be the cube root of y to the 4th, if you're in the denominator, I want you to go up. So 4 doesn't divide by 3. Don't break it down to y cubed times y like we did before. Instead, create more y's. I need, let's see, 4 doesn't divide by 3, but 6 does, so I need 2 more y's. So we're going to create more y's. So if you're in the denominator, we're going to go a higher exponent. If you're in the numerator, we take that 4 and break it down. But if you're in the denominator, we're going to take the 4 and create more. So we have the cube root of y to the 6th, which will be the cube root of, which will be y to the 6 thirds, which is just y squared. So to rationalize the denominator, if the exponent doesn't divide by the root, think about going up to a higher number so that it does get divisible, or so it is divisible by the root. If you're in the numerator, we're going to go down. If you're in the denominator, we're going to go up. So that's kind of a nice rule to follow. Let's see if we can follow this again. If it's together, you usually pull it apart. And if it's apart, you usually put it together. That's another nice little rule. So I'm looking to see if I could simplify anything, and I just can't. So I'll leave this. I can't reduce anything. So this is the cube root of 4 over the cube root of 5x to the, now I could break it down to cube, but then I'm breaking my rule. So I really don't want to break this down to be x cubed and x squared. Even though the cube root of x cubed is nice, I ended up with kind of a mess, and I would rather, if you're in the denominator, move up. So I'm going to keep this x to the 5th and y squared and think about how many more do I need. So I'm going to multiply by a clever use of a yellow number, which is equal to 1. So whatever I do to the denominator, I have to do to the numerator. So I'm going to take this fraction in green and multiply by a yellow 1. It's going to change colors to pink, but the pink will equal the green because I'm just multiplying by a yellow value of 1. So let's see, I've got 1, 5. I better create 2 more. That's the same thing as a 25 up top. I've got 5, doesn't divide by 3, but 6 does, so I need 1 more. So I have x to the 5th and an x, I can write it out for you if you don't see it. The cube root of x to the 5th times the cube root of x is the cube root of x to the 6th, and 6 does divide by 3, and it becomes an x squared term down here. And I'll do the same thing with the y's. 2 doesn't divide by 3, but I need to create one more y, and then I'll have the cube root of y cubed. And I have a 5 out there too, because I have the cube root of 5 to the 1st, and 5 squared is the cube root of 5 cubed, which is 5. So it looks like my value of numerator and denominator is the cube root. 25 times 4 is the cube root of 125. Or wait a minute, that's 100. Whoops. Let's try 100. 4 quarters is $1. I'm thinking if I can simplify that 100. So right now what I'm thinking is 2 cubed is 8, and 8 doesn't go into 100. 3 cubed is 27. I'm trying to look for perfect cubes that go in there, so 64 doesn't. And 5 cubed is 125, so I don't think I can simplify the cube root of 100. I wish I could, and I can't cancel that 100 and the 5 because one's underneath the radical and the other's not. I'm not sure if I could do anything else. Good, the author agrees. We're simplified. So again, the use of conjugate sometimes, which says change that middle sign, is a very helpful strategy in solving it. So the conjugate here would be the square root of 7 minus, changing the middle sign, and the square root of 7 minus. So up top, all I have to do is distribute, and I'll end up with 5 square roots of 7 minus 5y. In the denominator, I'm going to FOIL. So the first terms is the square root of 7 times square root of 7, which is 7. Your outer terms should be negative square roots of 7 times y. The inner terms is y positive, and that should just be 0. Because those terms are alike and you can combine those. The last term would be a positive y and a negative y, which makes negative y squared. So I think I'm done. 7 minus y squared. I can't factor anything out up here. No GCFs. And it looks like the author agrees. So the trick here is to multiply by a unique value of 1, and we call that the conjugate when you change that middle sign. This one we're going to multiply by the conjugate, which is the square root of 3 plus the square root of 5. Remember, it's a unique value of 1. And in the denominator, I get the square root of 3 times the square root of 3 for the first terms. And I don't even really need to worry about the outer and the inner, because remember, the FOIL method says they will cancel. So the first terms is 3. The last terms are going to be negative square roots of 5 times positive square roots of 5, which will give me negative square roots of 25, which I'll just write as minus 5. So it gives me a negative 2 in the denominator. The numerator I'm going to have to FOIL. So first terms is 5 square roots of 3. The outer terms is 5 square roots of 5, which I cannot combine. The inner terms is 3. And the last terms is the square root of 3 times the square root of 5, which is the square root of 15. And again, I don't see any terms that I could combine, so I'll just leave this as the final solution with a negative 2 in the denominator. Last example, I'm going to have to multiply by the conjugate, which says change the middle sign. I'm going to look at the denominator first. The first terms is 3 times 3, which is 9. The outer and the inner should cancel. You can look at it if you'd like, but I'll have a positive junk and I'll have negative junk, which same junk, which will cancel. So next I'm going to try to multiply the denominator together. A positive 2 times a negative 2. Breaking this down is just a negative 4, and the square root of x times the square root of x is just an x. In the numerator, when I do the FOIL method, the first term is 2 times 3, which is 6. The outer is negative 6 square roots of x. The inner is a positive 3, how about 9 square roots of x. And then the last term here is going to be positive 3 times negative 2 gives me a negative 6, and the square root of x times the square root of x is just an x term. So I think I can combine these green terms now. Negative 6 plus 9. And the reason why I can combine those because they're the like terms. But I can't do anything with the 6 and the minus 6x, so those stay there. But this green term turns out to be a positive 3 square roots of x all over 9 minus 4x. And I think that might be the final solution. Ooh, we got a 5 in there. Should have had negative 4 and 9. Ooh, this should have been a negative 4. How come? I'm so sorry. Let's see. This should have been a 2 times a negative 2 for a negative 4. So there's my outer terms. And the outer terms, I bouched. So sorry. So it should have been this pink term times this pink term gives me this pink term. So that should have been a negative 4. And negative 4 and 9 is going to change this to a 5. So 6 plus 5 square roots of x looks a little bit better. Minus 6 square roots of x all over 9 minus 4. Good. Here's how the author worked it out. You might want to look at his work, but he has the same thing. First, outer, inner, and last. I hope you found this video helpful. Please email me with your questions. Thanks.